version of this course, in the first several lectures, I explained some rough ideas of what we want to talk about. So I will try to remind you of some fundamental things and then give some precise definitions and ideas. We're dealing with manifolds. And when we have a manifold, I will usually denote it by M. Now, of course, this is a topological space. Which is much better than some just general topological space. So I'll go off. Maybe some axiom should be fulfilled for me here. Don't worry too much about this. The main point is that this comes equipped with an atlas. And an atlas consists of a bunch of pairs, so U alpha, Phi alpha, where U alphas are open sets in M, and M is a union of these U alphas. And Phi alpha gives you coordinates on U alpha. And at least at first, because I just said topological space, this is a homomorphism to some open set in Rn. So you should have the usual picture in your mind, which you do, I think. If you have a sphere or something, you have some open set U alpha, which you want to understand better, so you have some homeomorphism, as I always say, to some page here in the atlas, maybe Phi alpha. This is a page in the atlas, this is a homeomorphism. And I'm constantly saying diffeomorphism because this thing has a smooth structure. And when I use the word smooth, I mean C infinity. Key being that these covering is compatible, so the change of coordinates is in fact smooth. I'm just reminding you of the basic notions here at the beginning of this class. Change of coordinates is smooth. Again, when I say smooth, I mean as smooth as we need in the context, but to make it precise, C infinity. So that means that if I write it down, the change in coordinates is, in my notation, Phi alpha inverse Phi beta, mapping the intersection, mapping V alpha beta. It's a terrible thing, right? To V beta alpha. Right? So what you have to figure out, right, is here you have U alpha, and here you have U beta, and U alpha and U beta go to something in the plane, different things, and if you start with the intersection here and regard it through the alpha coordinate, that's what I mean, U alpha beta, and if you regard this intersection through the beta coordinate, that's what I mean, V beta alpha. Right? And then so you have this map going from the alpha coordinatization of V of that intersection to here. This should be smooth. So C infinity. Okay, so that's nothing new for all of you. And so we have C infinity structure, and the basic thing that we have from that C infinity structure is to every open set, and now I will just look at U to be an open set in the manifold. we have the C infinity function. For every open set, we have the C infinity functions. Now, I'm always making propaganda to make sure everybody looks at the algebraic structure. This is a commutative ring with identity. So this is a commutative ring. So what does that mean? It has exactly the algebraic structure of a vector space, except you should think that the scalars, well, you can add, excuse me, you can add and multiply. So this, let me just, so you can add functions and multiply them. This is really boring. So you have f plus g is an addition. It's abelian. So it's a commutative, and multiplication is also abelian, and it's associative. And so on. You know, so you check it out, and that's what a ring is. It's a commutative ring. Okay. So this is a commutative ring, and that's the basic ring for every open set that we discuss. Okay. So when you have such a ring, R, you have the derivations on this ring. Right? And we talked about this last time, the importance of derivations. We call these vector fields in this case, but just in a general thing, whatever it is. These are mappings with respect, which we respect the additive structure, but with respect to multiplication, you have the derivation rule. So if we take a derivation, say d of fg equals dfg plus fg, Leibniz rule. So we have such a wonderful thing like this C infinity ring, and we look at the ring of derivations. In the case for our C infinity functions here on an open set, then the derivations on this ring we know very well are called the vector fields on U. And there's a good reason why we call this a vector fields on U, because they classically look like vectors. And please be watching, we have a number of physics people here. If you ask a physicist what is a field, be very careful to pin the physicist down on what he's talking about, because it's not so clear. There are various interpretations. For us, vector field is, we know what it is, it's a derivation on this ring. So we know for in local coordinates, so if we have a local chart, a derivation on this ring, a vector field on U, if it's a coordinate chart, it can be written as a linear combination with functions as coefficients, fi dx dxi. I will use this notation constantly. Okay, so you're familiar with, well, you are familiar with this notation, I know that. But when I don't say anything, it means we're summing over this with the index. So if I did something like put some other thing here like alpha, then there's no place to sum over here, and so I would really be talking about something alpha, but I didn't put it for this. Okay, so in local coordinates, that's what a vector field is. This guy in local coordinates will be abbreviated as in this way. Yeah. So it's implicit that we should know that the coordinates are called x, and this needs the derivative with respect to x. Now, as you all know, you can evaluate a vector field at a point. In this place talking about where we have, it doesn't, well, at a point x in the manifold, or in the open set, or wherever the vector field is defined. And if this vector field x is a vector field, say on N, so it's a global derivation, or on an open set which contains this, we can evaluate it at a point. Really means you can differentiate any function which is defined near that point, and what this is you differentiate it and then get an answer. So keep in mind that that means this thing maps maps anything. If you have an open set U and any open set U and any C infinity function near that, I can differentiate it with respect to this vector field, and this means that you get a number. So what this derivation rule is, this thing on the product is no longer a function, it's a number, it's the evaluation of the function at x. This is what you do sometimes in calculus, times the derivation of g, let's be very precise, so at x of g, this is really boring, I know, so the derivation of f at x times g of x. So you get a number, real number. It's an evaluated derivation. And so what that says is that a basis for these things, for the such derivations at a point, was the same guys, namely ddx1 at the point, ddxn at the point. Right? So that's a basis, and in particular, you see, proving all of this, which we have done in some lecture or another, this thing, t at this point, x of n, these are such derivations at this point, is an n-dimensional vector space. It's not so clear. So that's a review of everything, just to set the language. And now, as you know how I always think in a picture, the manifold M is a base space of our discussion. Sometimes I call it the base space of the discussion. And for every x in the manifold, you have associated a vector space, namely the tangent space at that point. If you have another point, y, you have another tangent space at that point, and so on. The fundamental picture that makes the difference between beginning calculus and advanced calculus, which we're doing here, or mathematical physics, which you're doing, is these vector spaces are all different. These vector spaces are all different. There is no canonical way to say that vector space is canonically identified with that space. There is no canonical way to say that that vector space is identified with that space. The way to do it is given to you by the physics. The way to do it is given by some additional structure. So as I said last time, we're dealing with manifolds plus. And the plus part is some way to identify tangent spaces so we can differentiate and so on. Some additional structure. Now, this union of spaces is just these tangent spaces, the union of these spaces, this disjoint union. That's my picture. I stand, as you all know, I stand when they draw this picture. All this formal union like this, and I was telling Sandeep, because this has to do with the farmer in Nepal, someplace, is there is at least one section around here, it's called the zero section, that God gave us. In Nepal or Germany or wherever you're thinking, it doesn't matter. There's exactly one zero section, and that's it. There's nothing else canonical. That's it. There's nothing else canonical. Yes. You may take coordinates and you start writing sections, which I'm going to define now. What is a section? And you'll say that's good and you're happy, but it is not canonical, at least at this stage of the discussion. So we need a smooth structure here. On this tangent thing. And this tangent, this smooth structure is most easily defined by a frame. So so defined by a frame. So I have to remind you what is a frame. You talk to anybody, they'll talk about frames, they'll talk about moving frames, and that's what you're really talking about in dimension 3. The tangent, what's terrible about these tangent spaces, in R3, we have the tangent space at a point, and it doesn't look tangential because we put it in there. We put it with the Fußpunkt here, and that's the tangent space here. And you say, well, I like this frame here. Okay, good. You like this frame here, and you like this frame here. And the key thing is these frames from here to here are moving smoothly. And so, yeah, the way to formulate that. So, defined by a smooth frame. So it's just a basis of vector fields E1 through En, E. Sometimes in text I make that heavy to indicate that's a frame for some reason. So the I is a vector field on U, and E1 of X through En of X is a basis of Tx of M for all X. Right, so in dimension 3, you would never just take 2 vectors, you have to have 3 vectors. At each point you have 3 vectors, and these are moving in vector fields. So that's a very intuitive thing, right? 3 independent vector fields in R3, for example. On a sphere, you say, well, okay, I'm completely cool. I have a vector field here, 2 vector fields here on this sphere. Over here, I have 2 vector fields on this. I have a whole frame on that thing here. But you will never globally have a frame on S2. S2 does not have a global frame. Okay, you know that, that's famous. Everybody learns that in high school. Something about combing your hair, right? And you never, on a ball, you can never have everywhere 2 independent vector fields. That is a statement that the tangent bundle of the sphere is non-trivial. Okay. But on some open set, of course, you have the frame. We've discussed it here every place. So if you have a frame, these are a basis of this, and now this gives you a map. This gives you a map to U cross Rn, which is a vector bundle, vector space isomorphism on each fiber. Yeah, namely, V goes to, let me say, I said U cross, so V at X, so I think it's very convenient. V at X, you write a point in the bundle, V, and you indicate that it's projected to X, so it's at a Fußpunkt X. V at X has coordinates goes to its x, its Fußpunkt, and its coordinates. V, a vector, goes to its Fußpunkt and its coordinates. It tells you where it is. That's great, because that means this guy here, really, I know where it is if I know its Fußpunkt, and now I need to know its coordinates. Its coordinates with respect to this frame. So the coordinates with respect to the frame are C equals C1 through Cn, if you like. I think it should be a row vector. And it means that V of x is a linear combination. So C at C1 of V, E1 of x, to Cn of V, En of x. So that gives you an isomorphism, so that means even though this whole thing is perhaps not trivial, in the neighborhood of x, where I have a good frame, this part here is at least bijectively, and then using the coordinates, the smooth structure here, I bring back the smooth structure to here, and we see that it's compatible, and this gives it smooth structure over there. So a vector bundle is a union of vector spaces, which can be framed. That means over some open sets, you have a frame, and you have the smooth mapping to U cross Ra. Okay? You okay?
So
We need, yeah, you're gonna, let's think about it. Remarks? Yes.
yes. So is this so often you said in some of the previous lectures that a tangent bundle has a smooth structure that's compatible with the manifold.
In particular, it's compatible with the manifold, yes.
Yes.
That means, well, he said, I'm going to read, you maybe don't hear his question. He says it has a smooth structure which is compatible with the manifold.
Mm-hmm.
That, in particular, the upstairs space is a differentiable manifold, the downstairs space is a differentiable manifold, the projection map is a maximal rank morphism, and locally, by a frame, it has these beautiful coordinates. And these beautiful coordinates respect the vector bundle, the vector space structure of the fibers. Right? I mean, this map is not just some coordinate chart. It's a map that takes the vector spaces here, which are just vector spaces somehow or another, but into the usual vector spaces of Rn. So it's a moving basis in this bundle. Is that okay?
Yes.
Yes.
So all the CIs there lie in the cotangent space? Because all the CIs there, right? They lie in
Oh,
the
yes,
cotangent
okay,
space.
so yes, that's very good. So remind me to say that in a minute, okay? He says that, I really underline this business about if you have a basis of a vector space and you take a vector, right? Then you express it in coordinates with these coefficients. These coefficients are linear functions on the vectors. So they're elements of the cotangent space, of the dual space. So we have vector space and dual space. Okay? Other points? Good. I think we're all fine with that now. So that's the tangent bundle. And it has smooth structure as above. And a vector bundle in general, so a vector bundle in general is just and I'll repeat exactly what I just said to you. You think of your favorite tangent bundle if you like, but there is a covering of the base. So upstairs is a differentiable manifold, downstairs is a differentiable manifold. There's a maximal rank surjective map from upstairs to downstairs. The fibers are all vector spaces. It's not enough. is locally trivial. I think it's not enough. You should check to see what more you need to prove that it's locally trivial. It's close. Again, smooth upstairs, smooth downstairs, maximal rank surjective map. All fibers are vector space. Yeah. But it's locally trivial. That means you have a frame downstairs. That means for n maps into the bundle space, E1 through En. Yes? So that the map given by those n maps is a coordinate chart. So it is an isomorphism onto the base cross Rn. Right? And that gives you the smooth variation of everything. Right? So I think you need that map. But maybe you get it free. I'm not sure. You understand what I'm saying, getting it free from the differentiable thing going on. It's close. I've forgotten. I thought about this a long time ago. But so in general, it's a vector bundle. In general, smooth. It means smooth upstairs, smooth downstairs. The map P, pi, from upstairs to downstairs is smooth, maximal rank, surjective, all fibers EX are vector spaces. So there's a vector space structure on each EX, and frames exist on a covering of the base. Right. Okay. That's a vector bundle. Okay. Yes, ma'am.
So what's a covering of the base? What do you mean by
Open covering.
Okay.
Oh, I understand. You see, that could be, I could have made a very mysterious statement there. I could have meant after you do an unramified covering of the base, you have something like this. I mean by that an open covering of the base by open subsets. Right? Yeah. But it, right. By open subsets. Okay. Okay?
So what are E and B again?
Yeah.
What are E and B again? I mean, what are E and B? I mean, isn't just
E and B are differentiable manifolds.
yeah.
Pi is a smooth map of differentiable manifolds. Pi has maximal rank. That means that rank at every point is the dimension of.
Oh, it's in general definition.
I just wrote a general definition.
There are many differences.
No?
In our case, E is TM and B is M.
In the tangent bundle case, yes. But of course, Abik just mentioned there's another one right off the top, and she's been talking about it all the time, the cotangent bundle.
Yeah.
So there are many bundles of interest, and we've met several of them here already. Okay. So the first two examples. Is the tangent bundle we talked about as Malcolm just mentioned, is a tangent bundle, and a cotangent bundle is the dual bundle. So that means that the frame it's going to be, each fiber is going to be the dual space of the other fiber, and it means that the frame of this thing is going to be the dual frame. Okay, so if you have a frame on the tangent bundle, you need to write down the dual frame. Now everybody here knows that if this is a frame on the tangent bundle, on some open coordinate chart, for example. So this is a frame on the tangent bundle, say over U. Then we have the dual frame of the cotangent. Over the same set. Right? That's right. And you all know what that means. That's the definition of dx. That's, in some sense, the definition of dx. Leibniz would have liked this problem. So this means dxi of delta of this thing is delta ij. It's the dual base. Okay. So people have different notations for that, but my notation is these are the elements of the tangent bundle, these are the cotangent bundle. Okay. Those are the first two examples. And now I've done nothing. This is just manifolds and the basic stuff that exists on manifolds. The key, maybe a key remark is this, that I do not believe was serious, and now after even working with physicists, I now realize it's a very serious remark. So I was sitting in a lecture with a mathematician whose name you know, named John Tate, and he was explaining the importance of K-theory, algebraic K-theory, and I couldn't believe that that's important because it's too abstract and he could never compute anything. But this was about 30 years ago, and now we can compute a lot in K-theory. And there is a morphism here. It's probably this morphism, you guys will like this, it's called a functor maybe. So this functor takes a manifold maybe to K of that manifold. And maybe I write here C infinity because it's a delicate point. This is an object originally maybe in topology, but then moved into algebra. And of course, I use this in smooth or holomorphic setting. And I mean by this, in this case, when this thing is, this means the space of C infinity vector bundles on M. Okay. You gotta believe that's an important space. Yes. You gotta believe that's an important space, and you gotta believe that this should somehow tell you all about M if you do this thing. And then you start asking, well, what's the structure of this thing? Well, can I add two vector bundles? Yes. Can I multiply two vector bundles? Yes. Etc., etc., etc. These guys even subtract two vector bundles, just like, and when I saw that, I said, you have to be crazy, man. You're subtracting off. What does minus a vector bundle do? Well, it's not, okay, inverse vector. I don't know what that means. Yes? But it's a virtual bundle. And you should be happy with subtracting stuff off because you do it with 3 minus 4 is equal to minus 1. You do it all the time. So these guys, Grothendieck, for example, did this and said, you got this virtual bundle minus a given vector bundle. So this thing has all sorts of algebraic structure. It's very, very important and related to M. And I've actually had joint papers with physicists where we really use K of a certain object. Okay? So don't disregard it just because it looks terribly abstract. It's some sort of thing that takes the setting of manifolds, maybe you would say the word category, into the setting of vector bundles. Yeah. And you know, these children say, oh, vector bundles are so complicated. And you say, it is derived. The set of all manifolds is much more complicated than the set of all vector bundles. Because this thing forgets, in principle, something, right? It only looks at the vector bundle. Yeah. It's like saying a cohomology theory, oh, it's so complicated, cohomology theory. A manifold to its cohomology theory is much simpler than the manifold, right? Okay. So one of the key things that we do with with these guys is we differentiate sections of the vector bundle. I have not explicitly said what a section of a vector bundle is. So, connections differentiate sections of vector bundle. I've talked about this in the previous lectures, but only roughly, and now I want to be more precise. Okay? And I also want to seek people to bring the connection to what you're looking at as Christoffel symbols and so on. So you can say connections, it's also Christoffel symbol, but you really want to know what this really is going on. Okay? Okay? And I strongly believe that it's very important to understand the background algebra of these spaces. Again, I am not a believer in pushing algebra for its own sake, but I'm a strong believer in looking at the algebraic structures on spaces and using this algebraic structure, understanding what's relevant. Right? If you don't do that, you've forgotten too much, and you really should look at the algebra. What is the algebraic structure? Right? For example, on K, what is the algebraic structure? That's interesting. I just told you it's interesting to talk about minus a bundle. Connections differentiate sections of a bundle. So what is a section? A space of sections of a bundle. A space of sections of a bundle over a metal. So this is the space of sections. Of E. Oh, I'm sorry, it's, I think it was multi, let's be careful. We always have B for the base and E for the upstairs, okay? This is old notation, I use old notation. B is downstairs base, E is upstairs entire space. Okay. Of E. Space of section. Well, S is such a section means S is simply a mapping of the base into total space. Well, there are lots of mappings of the base into the total space. For example, the base is a manifold M here. You could do something really stupid, right? You could do the most stupid thing. You could take the M and map it all to a point, right? Say we map M all to this point here. That would mean that this point here would go to that point, this point here would go to that point. But we don't mean that. We mean that a point goes to a vector in the fiber above it. Yes.
So S goes from B to N, right?
Have I written something? This is Colin was telling me this yesterday. Okay. Sorry. It's what happens when you get old. Other things happen also, but I don't want to talk about it. So, okay. So, no, the gap becomes, certain intervals in thinking are quite good when you're older. They're even better than when you're young. But then they're gaps, particularly in notation. Okay. So you don't want that kind of stuff. You want a point in the base goes to some point in the fiber. And that means it's really a section. But you should never write anything as a set. You should always write it as a map. Okay? So it's a map from the base to the total space. That's a section of the bundle, such that S maps a point to the fiber above it, and you can easily say that just by, if you project it back down, you get the identity on the base. Okay, that's clear. That's a section. And we talked about this last time. I think it's completely clear to you. The vector fields on the base is the space of sections of the tangent bundle of the base. that's the motivation for us. For example, the differential one forms on the base. That's the space of sections over the base of the cotangent bundle. So to each point, it gives you a cotangent vector. So these spaces of sections are very important. Okay. And again, I scream at you, what is the structure of the space of sections? Well, so you start to look. You're sitting in Nordmetall in your room and looking at this beautiful weather, and you're listening to some nice music, and it's daytime, you haven't yet had a glass of wine. And you want to talk about the structure of this, the space of sections of a vector bundle over a base. And so, you have courage to be stupid. You say, if I take two sections, what can I do? S and S hat. What can I do with two sections? Can I multiply two sections? No. Because that would mean I would multiply them in each fiber, right? And I don't know how to multiply vectors. Now, by the way, Grossman himself, who is also a high school teacher, sat in his office in a high school and tried very hard to multiply. He did not you understand yet how to multiply vectors. But of course you can multiply vectors abstractly, but you don't land in the same space, right? The product of two vectors is in some other space. You have to think of the product of two vectors as a tensor, right? Some abstract thing. But you, of course, if you have a section, what can you do with that? Multiplying is a bad guy. But one thing you can certainly do is you can take linear combinations. Everybody sees that, A and B, in the real numbers. All right, I have a section, and at each point it's a vector, and I just add the two at each point. Or multiply the first one times 2 and the second one times 4 and add or something. That's a trivial operation, right? Yeah, but the thing is, you would think of that sitting in Nordmetall, and then you should have another cup of coffee and say, you know, I forgot something. I forgot that if you have two sections, that I can add the two of them and multiply by something, but this something can depend on the base point. Right? What do I care if in one fiber I take a linear combination and then I start moving the linear combination? Now, okay, it better be good because these things should be reasonable functions, so they should be smooth functions. Right? At one point you can take a linear combination, at another point a linear combination, but this linear combination must vary smoothly because the sections must vary smoothly. Okay. So the big boy and girl, okay, physics is okay on this. The big boy and girl word for this is that the space of sections of a vector bundle is a module and maybe I'll call this script M for now because I want to talk about it abstractly, is a module over the ring R. So it is a so-called R module, which in this case is just the ring of C infinity functions on the base. Yeah.
I think it should be switched, should be
You know you're so quiet and I'm so deaf. So
I
what?
think it should be lambda of EB, not lambda of BE.
Probably I'm making, where are you saying?
Lambda of BE should be lambda of EB. We have different notation.
Oh, yes.
Same above.
So the differential forms, oh yeah. B. That's another thing that happens with A. It's called the important group of order 2. Right?
Oh, that's fine.
The important group of order 2
That was
acts on everything I do.
perfectly correct. That was all right. That was perfectly fine.
This is okay.
No, but it was okay before you erased it.
Vector, the sections over B of the vector bundle E. That's
So then change that.
Then change this.
same mistake.
Well, change that to the-
I want to write it this way. The sections over B, you just have to say it right and then you can write it right. The sections over B of the vector bundle E. Yeah, okay, did I write it wrong here some other places? I know, thank you for catching this. What,
The vector spaces over B is gamma of B and then TB, right?
so did I write gamma wrong? Where's gamma here?
Vector
Here.
fields over B. The gamma, no, the gamma.
The sections over B, yeah, I'll try to say it each time. The sections over B of the tangent bundle B. Yeah, the tangent. Yeah.
And then when you write the cotangent spaces, then it should be the other way around.
No.
No?
Sections over B of the cotangent bundle. So first comes the base, and then comes the bundle you're talking about. Yeah? And I probably should.
No, that was.
I mean, everything is inverted here, right? Where's another? That's okay.
Yeah,
That's okay.
yeah.
Something wrong down
Now
here?
everything's fine.
Am I good now? That's a bad English, I just hate that, but everybody says it. Are you good? I'm good. Yeah, okay, everybody's good. Okay. Thank you very much, I'm sorry, it's just terrible. Okay, but if you say it right, it's good. Sections over B of the bundle E. Okay. Okay? And the sections over B of the bundle E is a module M over the ring R. That means that you have a this ring is wonderful, it's a community ring, I just talked about it. This thing here, this thing is an abelian group, it's all wonderful, but much better than that, you have a multiplication operation, which if you have a function and a section, you can multiply the section by the function. Right? That means in each fiber, you're multiplying by a number, but this number is varying. It's fundamental that this is allowed, okay?
Then shouldn't R be C infinity of R? Because, I mean,
The ring is the coefficients that you're using to multiply, and this ring is the C infinity functions on the base.
because the base and then you took the base of a number, right?
Yeah. Yeah. It's what I talked about here. These coefficients are numbers at each point, but these numbers are varying in a smooth way. So the section is still smooth and it's wonderful. Okay? Okay, for a vector field, you know this. If you have a vector field and a function, f, then f times x is still a vector. Okay? Now you will hear about, if you're learning some algebra here at Yakos, you will certainly hear about modules over rings. And this is the genesis of it. This is where it comes from. These things come from important things like this. Okay. Now, we have the following thing. The derivations of the ring. Okay. What are the derivations of the ring? I told you what the derivation, there's someplace on this blackboard, I can't remember what I've done, but the derivation on the ring is the derivation satisfies the Leibniz rule. Right? Some ring, by the way, these can be really completely different kind of rings than you're talking about here. I know some of you interested in algebraic geometry, other places. These can be very rigid things. Okay. So they appear throughout mathematics, these modules over a ring. It is a vector space, except the scalars are functions. Right? The scalars you're using to multiply some are not just numbers, they're functions. Right? And so you have to be careful. Okay. You see, if they were just numbers, these derivations wouldn't do anything, so it's not very interesting. So this is the derivation rule. Okay. And now, given such a derivation, I want to associate to it a first order differential operator of the module, mapping the module to its set. I'm sorry, I'm being abstract. Absolutely intentionally. Okay? You know how to take derivatives on the ring, and you want to transform this notion of taking derivatives on the ring to the module. Again, isn't that what you would like to do? You know what's going on with taking derivatives of C infinity functions. You would like to know how to take derivatives of sections of the vector bundle. Do I have to say it any more explicitly? Yeah.
What's diff 1 and
First order linear differential operator. So I'm going to say it. Okay. Okay. I'm going to say all of this precisely, but it is written down in physics notation in some stupid calculation that I hate, that I have to lock myself up in a closet for a week at least to do a calculation. Yeah. I hate it. Yeah. But I want to know what the devil it is. Okay. Again, I know how to take derivatives of functions. I do not know how to take derivatives of sections. That's the whole thing I've talked about here for 3 lectures. There is no way to take derivatives of sections without additional structure. I've told you, okay, my Frederick, 5 years old, says, well, you just translate over to this fiber, you pull back that thing here, you take the difference and divide by h, and you get a derivative. Yeah, well, there's no such thing as translate over to that fiber. No such thing. Right? So again, we are interested in starting here with some reasonable derivation of the ring and getting a derivation of the module. Starting with a derivation of functions, getting a derivation of sections of the bundle. Okay? Okay. And this should be an R module morphism. So this would be R module morphism. And this thing, I will use classical notation, call it nabla. Okay. So a nabla takes a derivation on the ring and tells you how it acts on sections. Right? It takes a something on like a vector field and tells you how it acts on sections. Nabla of x, we write this way. This is another notation for nabla of x, acts on sections. It acts on M. It acts on M as a first order differential operator. What is a first order differential operator? A first order differential linear differential operator acts like a vector field. So, these first order differential operators are the form nabla of x of f times the section is f times the nabla x of the section. And now I have to say what x does on the function. Well, I know that x is a vector field. Okay? You don't like me, Crystal. I'm sorry, I try to be nice. Yes?
So the ring is...
She likes me, but she's asking all these questions that are very good and making me mad.
So the ring we're talking about right there is C infinity of B.
That's right. But what I've written here has nothing to do with C infinity. It's just you have a module. So it means the coefficients are not necessarily scalars. Module over a ring. So you can I use the letter F to remind you maybe it's a function, but maybe we should use the letter R in the ring. So what's allowed here is R times N, right? R times N, okay? So given a derivation on the ring, I need to know what the derivation on the ring is because I'm going to have to do it here. This is the derivation part on the ring. I need to know what that is. So it's a mapping. I give you a derivation on the ring, like a vector field, and I've got to tell you how it acts as a differential operator on the module. First order. First order means it's just first order vector differential. Okay? Okay? That's no confusion. You're not confused. No? Yeah? No confusion. Ring, module, derivation on the ring, transported to differential operator on the module. It makes sense. I mean, you have, right? Vector field, you want to know how it acts on sections. Okay? The thing is,
So S there is a section.
yeah, yes, S is
S is a section, so how does
so,
nabla sub x act on S? Or is it,
so,
or are we multiplying them?
okay, let me, I think I've written enough here, but I'm going to write it in other notation, and I think you'll like it. It's really worth doing this, okay? Okay. So, so nabla of delta. I'm going to not call it x anymore. Just a derivation. Professor Penkoff doesn't like vector fields. He likes derivations. He says algebra. So nabla of delta is something here. So this is a module. So I have to tell you what it does to something if I multiply it by something in the ring and something in the module. Right? What is it?